Dear class 10 students, today we are starting the first chapter in your mathematics, which is real numbers. So I am starting the chapter real numbers with one famous principle which is popularly known as Euclid's division lemma. So Euclid's division lemma. What is Euclid's division lemma? Here I will clearly explain with examples. You please observe carefully. See, if A and B are two positive integers, when A and B are two positive integers, then there exist the integers Q and R. There exist the integers Q and R such that A is equal to B into Q plus R, where zero is lesser than or equal to R is strictly lesser than B. This condition should satisfy altogether. Please do remember. So when A and B are two positive integers, then there exists the integers Q and R such that A is equal B into Q plus R, where this particular R has some specific limits that it should be equal to 0 or more than 0 or lesser than B. It should be equal to 0 or more than 0 and lesser than B. Strictly lesser than B. Strictly lesser than B. So please understand. So this property is known as, this theorem is known as Euclid's division lemma. So see here what the Euclid is trying to explain is, he is trying to explain the division process verbally using words and symbols. He would like to explain the division process, but it is after all the division only. See, for example, here what he is trying to say is A is a positive integer. See, when you have divided A with B, so there will be some quotient. That quotient is Q. And at the end of the division process, you get some remainder. He is denoting it with R. And this remainder is 0 or lesser than the divisor. See, the division principle only, the division principle. So he is expressing as a theorem. So this is called Euclid's division lemma. So by taking A, B, Q and R, so you got like this. Suppose if you have observed with an example, suppose when 35 is divided by 7, say for a moment, 7 5s are 35. Then the remainder is 0. Then according to Euclid's division lemma, 35 is equal to 7 into 5 plus 0. It's the same thing like dividend is equal to divisor into quotient plus remainder. The same thing in other ways explaining, right? So now let us take another example. When 3 is divided by 8, say for a moment, when 3 is divided by 8, even 8 ones also 8 crosses 3, so you cannot even take 8 ones also, you have to take 8 zeros are 0, then you get this 3. That's why here he is saying that a and b are two positive integers, but here he is just saying q and r are integers, so they may be 0 also. So q may be 0, r may be 0. That is why he is not insisting positive integers, but a and b are positive integers, q and r are just integers. Okay. So when 3 divided by 8, then the quotient is 0. Okay. Then 3 plus 0 is 0. So then 3 is equal to, like a is equal to b into q plus r. So 3 is equal to 8 into 0 plus 3. Understood? See, always this r is 0 or lesser than b. Please try to understand. Always this remainder is either 0 or lesser than the divisor. So please do understand. This is Euclid's division lemma. So I'll explain this lemma taking the last example now. So you are dividing 25 by say 6 for a moment. Then 6 4s are 24, the remainder is 1. So 25 is equal to 6 into 4 plus 1. This remainder is lesser than divisor. Remainder lesser than divisor, or at least remainder is 0. So this is what Euclid's division lemma. So Euclid's division lemma is nothing but a division principle. So if a and b are positive integers, then there exist integers q and r satisfying the relation a is equal to b into q plus r, where r has limits 0 less than or equal to r, strictly less than b divisor. Okay. Now we'll solve some theorems relating to Euclid's division lemma. These are most important. For example, show that any positive integer is of the form three p or 3p plus 2. So we are required to show that any positive integer is of the form 3p or 3p plus 1 or 3p plus 2. So how do we prove? See here, proof follows. This theorem. Proof. So let a be any positive integer. Let a be any positive integer for a moment, and b is equal to 3. So a is any positive integer and we are taking b is equal to 3. Therefore, by using Euclid's division lemma, what do you get? Just now we have discussed now. So Euclid is using division lemma, we get therefore A is equal to 3 into some P. Here he is using P, so we can use P here. In Euclid's division lemma we have used Q. As he is using P, you can use P. So the letter has no problem. Okay, changing letter has no problem. So we are taking A is any positive integer and B is equal to 3. Then by applying Euclid's division lemma, just now we have discussed, then you get A is equal to 3 into P plus R, where R has strict limits, that is 0 is lesser than or equal to R is strictly less than B. What is B here? 3. So R is strictly less than 3. So 0 is less than or equal to R is less than 3. Therefore R values are taken as 0, 1, 2, that's all, because it is strictly less than 3. So now when R is equal to 0, you get A is equal to 3P. Now when R is equal to 1, you get A is equal to 3P plus 1. And when R is equal to 2, you get A is equal to 3P plus 2. So that's it. Thus you can conclude that any positive integer is of the form 3P or 3P plus 1 or 3P plus 2. Did you understand? Now next theorem is show that the square of any positive integer so that the square of any positive integer is of the form 3m or 3m plus 1. Show that the square of any positive integer is of the form 3m or 3m plus 1. Now this is another theorem. So now proof. So let A be any positive integer then by previously proved theorem, any positive integer will be in the form of 3p or 3p plus 1 or 3p plus 2. So by a proved theorem, A is equal to 3p or 3p plus 1 or 3p plus 2. Any positive integer is of the form 3p or 3p plus 1 or 3p plus 2. Just now we have proved. So now let us take A as 3p in case 1. Now because in the problem the square of the positive integer is involved, let us square on both sides. Squaring on both sides, A square is equal 3p whole square plus A square is equal 9p square. So this implies A square is equal to 9p square, which is equal to 3p into 3p. Right? Right? So A square is equal to 3p into 3p, which is equal to A square is equal to 3 into 3p square, which is equal to 3m. Here 3p square I have considered as m, where 3p square is equal to m. So we have to prove that the square of any positive integer is of the form 3m or 3m plus 1. Now here we have seen the square. When a is equal to 3p, we have seen the square, and that square we got as, that square has finally took the form 3m. So now let us go for 3p plus 1 in case 2. This is case 1. Now case 2. Now let us take in this case a as 3p plus 1. So if you take a as 3p plus 1, squaring on both sides, you get a square is equal 3p plus 1 whole square. Now you expand this using a plus b whole square formula. Then you get 9p square plus 6p plus 1. And from here to here, if you take 3 common, okay, then it would be 3p, right, plus 2 plus 1. So I took 3 common from these two terms. So I got 3 into 3p square, because here square is there. So 3 into 3p square plus 2p. I took 3 common. So 3 into 3p square plus 2p plus 1. Now you consider this as m. So which is equal to 3m plus 1. I considered 3p square plus 2p as m, where 3p square plus 2p is equal to m I considered. So now finally that square has been reduced into 3m plus 1 form. Understood? So even in the case of 3p plus 1, okay, we have seen the square. So that square is in the form of 3m plus 1. So now at last we will see in the case of 3p plus 2, as it is case 3. So a is equal to 3p plus 2. So if you square it on both sides, you get a square is equal 3p plus 2 the whole square plus a square is equal 9p square plus 12p, using expanding in a plus b whole square form, 12p plus 4. Did you understand? So it is 9p square plus 12p plus 4. Now this is equal to, now what we shall do here? So here what we shall do here now? 9p square plus 12p. Now you write 4 as 3 plus 1. 4 can be written as 3 plus 1, right? So now from here to here take 3 common, just 3. Then you get 3p square, right? 3 into 3p square, 9p square plus 4p plus 1, bracket close. I took 3 common in these 3 terms. So we get this outside plus 1. So now this is in the form of 3m plus 1, where according to me m is equal 3p square plus 4p plus 1. So in all the 3 cases, okay, the square is taking the form either 3m or 3m plus 1. So the theorem is proved, right? So next theorem is we have to show that one and only one out of n plus 2 or n plus 4. One and only one out of those three is divisible by 3. That means if n is divisible by 3, the remaining 2 cannot. Similarly, if n plus 2 is divisible by 3, that first and last cannot. Like that. So, show that one and only one out of n plus 2 or n plus 4 is divisible by 3. So, we are going to prove that. So, we know that here what is n? Here n is positive integer. So when n being positive integer, one out of those three is divisible by 3. That's what we are supposed to prove. So we know that any positive integer is of the form, we have proved this, 3p or 3p plus 1 or 3p plus 2. So, every positive integer is of the form 3p or 3p plus 1 or 3p plus 2. Right? Now, first I am choosing n as 3p. Now, let n is equal to 3p. Let n is equal to 3p. Obviously, this 3p, which is a multiple of 3, so obviously it is divisible by 3. Is divisible by 3 clearly. So now let us take n plus 2. Now we have to prove this n plus 2. Neither n plus 2 nor n plus 4 is divisible by 3 because already n is divisible by 3. Because we took 3p, it is a multiple of 3, it is divisible by 3. So n is divisible by 3. So by the theorem, only one of them is divisible by 3. So already you are agreeing n is divisible by 3. So the other two are not divisible by 3. That we have to prove now. So now n plus 2. N plus 2 is equal to, what is n? It is 3p. It is 3p plus 2. Are you following? So this is equal to, now here what it is giving the information, when n plus 2 is, because this is a, if you compare this with Euclid's division lemma, this is a, this is b, this is q, this is r, right? Now, when n plus 2 is divisible by 3, divided by 3, when n plus 2 is divided by 3, you are getting the quotient p and the remainder r. Did you understand? So when n plus 2 is divided by 3, you are getting quotient p and remainder 2. Means when you are dividing n plus 2 with 3, it is leaving some remainder. Right? So it is very clear that therefore n plus 2 when divided by 3 leaves the remainder 2. It means that n plus 2 is not divisible by 3. because it is understood. When n plus 2 is divided by 3, you are getting the remainder 2. So n plus 2 is not divided by 3. So we have proved n plus 2 is not divided by 3. Now let us see for n plus 4, right? So now I am taking n plus 4. We took n as 3p plus 4. Here you cannot take 4 because this if you take this as r, okay, it should be lesser than b, but the b is 3 here, r is 4, r is always lesser than b, so you cannot take 4 as this. So what you have to, a small change you have to bring. So here you write this as 4, you write as 3 plus 1. Now you take 3 common from these two terms, then you get p plus 1 plus 1. So what now, what does this equation is giving as the information if you use Euclid's division lemma? So it is giving you the information that is when n plus 4 is divided by 3, leaves the remainder 1. Therefore, when you are getting some remainder, what does it mean? N plus 4 is not divisible by 3. Understood? So, in the case 1, when we took n as 3p, itself divisible by 3, 3p itself divisible by 3. So, the other two numbers n plus 2, n plus 4 are not divisible by 3. We have proved now here. So, now let us go for another case. So, now let us choose n as 3p plus 1. This is the second case. So, any positive integer is of the form 3p or 3p plus 1 or 3p plus 2. We have proved this theorem with 3p. So that chapter closed. Now we will prove with 3p plus 1. Next we have to prove with 3p plus 2. So if we have finished all the rounds, our problem is finished. Now let us take n as 3p plus 1, case 2. That is by Euclid's division lemma. So what you can write, that is when n is divided by 3, when n is divided by 3, leaves the remainder 1. That means n is not divisible by 3. So we have proved n is not divisible by 3. So this first one is not divisible by 3 when n is equal to 3p plus 1. Now let us see the second one, 3n plus 2. So now n plus 2 is equal, what is n? n is 3p plus 1, bracket close, plus 2. So which is equal to 3p plus 1 plus 2 is 3. Now take 3 common, 3 into p plus 1. So it is a multiple of 3. So it is divisible by 3, which is divisible by 3. So here when n is 3p plus 1, our n plus 2 is divisible by 3. Now let us see now n plus 4. So now if you take n plus 4, whereas n is 3p plus 1 plus 4. which is equal to 3p plus 5, in fact, which is equal to 3p plus 3 plus 2. So which is equal to 3 into p plus 1 plus 2. Did you understand? So what does it mean? It means that when n plus 4 is divided by 3 leaves the remainder 2. That's what you are getting the information. Therefore, what does it mean? N plus 4 is not divisible by 3. So, in the case of n being 3p plus 1, n is not divisible by 3, and the second one, n plus 2, is divisible by 3, and again the third one is not divisible by 3. So, one of those three quantities is only divisible by 3 even in second case. Now, let us go for the last case. What is that? N is equal to 3p plus 2. So, when n is equal to 3p plus 2, that means when n is divisible by 3, leaves the remainder 2. That means n is not divisible by 3. So, the first quantity n is not divisible by 3. Now, let us see for n plus 2, which is n is 3p plus 2 plus 2. So, which is equal to 3p plus 4, which is equal to 3p plus 3 plus 1, which is equal to 3 into p plus 1 plus 1. So, what does it mean? Leaves the remainder 1. So, when n plus 2 is divided by 3, leaves the remainder 1. Therefore, n plus 2 is also not divisible by 3. So, in the case 3, when n is 3p plus 2, we have seen that n is not divisible by 3, and we have seen that n plus 2 is also not divisible by 3. So, now we have to see that n plus 4. Now, n plus 4 is equal to, n is 3p plus 2 plus 4, which is equal to 3p plus 6, right? Okay, right? Now you take 3 common. So it is p plus 2. Okay, that means 3 into p plus 2 plus 0. That remainder is 0. What does it mean? It is divisible by 3. So this is not necessary to write, just I am showing. So n plus 4 is a multiple of 3, therefore n plus 4 is divisible by 3. So, in this case, when n is equal to 3p plus 2, n and n plus 2 both are not divisible by 3, only n plus 1, n plus 4, the last one, n plus 4 is divisible by 3. So, in all cases, we have proved the theorem. So, finally, we can conclude that hence the theorem. Understood? Now students, we are learning how to find HCF using Euclid's division lemma. Right? So find the HCF of the following numbers. Using Euclid's division lemma. See, that first pair of numbers I am taking as 117 and 45, right? 117 and 45. First question. Means we are supposed to find the HCF of 117 and 45. So, take 117 is equal to, what is 45 into 4? 4 5s are 20. It is crossing 117. Now take 45 into 3, 135. It is crossing 117. Now you take 45 into 2. It is 90. So like this you can go into rough work and you can check. So 117 is equal to 45 into 2. 45 into 2 is 90. So how much has to be added? 27. So using Euclid's division lemma, 117 is equal to 45 into 2 plus 27. So it's nothing but like division, you see. Alongside you can even perform the division. When 117 divided by 45, then 7, so you get the remainder 27. So you get the remainder 27. Now the 27 has to be divisor and the 45 should be the dividend. Then 27 2s are 54. So you can only take 27 1s are 27. Right? Now 15 minus 7. It is 8. So 3 minus 2, 1. So now if you perform this here, now 45 is equal to 27 into 1 plus 18. Right? Now 18 should be the divisor, the 27 should be the dividend. So 18 ones are 18. Then the remainder is 9. You perform that here. Now 27 is equal to 18 into 1 plus 9. Now 9 should be the divisor, 18 should be the dividend. 9 to the 18. 0. The remainder is 0. So now here 18 is equal to 9 into 2 plus 0. In which step the remainder will be 0? In that step the divisor has to be taken as HCF. So the divisor is 9. So in the step where the remainder is 0, the divisor is 9. So the HCF of 117 and 45 is equal to 9. So you need not to perform that, only for sake of your better understanding purpose I have written this. Okay, you can, even if you do also, there is no any wrong. If you don't do also, there is no any wrong. Only thing, you should be able to proceed this perfectly. See, 117 is equal to 45 into 2 plus 27. Next 45 is equal to 27 into 1 plus 18. Next 27 is equal to 18 into 1 plus 9. Next 18 is equal to 9 into 2 plus 0. Are you following? So now let us do one problem without doing that parallel work. Okay? So that it will be very clear for us and you will get some confidence also. Okay? Now, find the HCF of, the second problem is, find the HCF of 210 and 55. So now solution using Euclid's division lemma. So now you see, let us not do this parallel work. Let us just directly face this. Now take the larger number. Larger number is 210. So 210 is equal to, now 55 into 3. 3 5s are 15. 3 5s are 15 plus 1, 16. 165. 210 is equal to 55 into 3, which is 165, plus, now you subtract 165 from 210. 10 minus 5, 5. 10 minus 6, 4. So 210 minus 165 is 45. So plus 45. So 210 is equal to 55 into 3 plus 45. Understood? Now 55 is equal to, next step, 45 into 1 plus 10. Do you agree? 55 is equal to 45 into 1 plus 10. In the next step, 45 is equal to 10 into 4 plus 5. Do you agree? Next, in the next step, 10 is equal to 5 into 2 plus 0. Right? So 10 is equal to 5 into 2 plus 0. Now, in which step you got the remainder 0? In that step, divisor would be the HCF. So the HCF is 5. So the HCF of 210 and 55 is 5. See, now here we have easily solved without doing that parallel division method. Just you can easily do in this way. Only thing is you have to do 1 to 3 problems so that you will get accustomed. Suppose in any case you got a confusion. So for example, I am suggesting for little slow students, suppose in any stage you got any confusion here, you can go for long division parallelly also. There is no any wrong. Okay, you can happily proceed. For sake of your confidence, I am doing one more problem. Find the HCF of 4052 and 12,576. So this is last problem under this heading. Find the HCF of 4052 and 12,576. Using Euclid's division lemma, right? So now solution. Now in solution, first let us take the larger number, which is 12,576, right? So 12,576 is equal to 4,052 into 4. You cannot do because it goes into 16,000. So now let us see 4,052 into 3. 3 2s are 6, 3 5s are 15, 1 12. So 12,000, you are getting 12,156 you are getting. But this is 12,576. So it is a lesser quantity only. So you can take 4,052 into 3. This is 12,156. Now from 12,570, little calculations will be there sometimes. So you should not feel afraid of in doing calculations. Now 12,000 from 12,576. Now you subtract 12,156. So this is 0, this is 2, this is 4. So you are getting 420, right? 420. So plus 420 this. So 12,576 is equal to 4,052 into 3 plus 420, right? Now 4,052 is equal to, right, 420 into, let us see, 420 into 9. 0, 8, 3780, right? So now 420 into 9, which is 3780. Now subtract 3780 from 4052. Then you get 2. 15 minus 8, 7. Next year you get 9. 9 minus 7, 2. So 272. So plus 272. Did you understand? Next now 420 is equal to 272 into 2. You cannot go. So 272 into 1. Now from 420, subtract 272. So 10 minus 2, 8. So 1. 11 minus 7, 4. Right? 3 minus 2, 1. So you get 148. So plus 148. Are you following? So now 272 is equal to 148 into 1 plus. Now from 272 subtract 148. So now 12 minus 8, 4, 6 minus 4, 2. 2 minus 1 1 124. So now 148 is equal to 124 into 2 plus 0, right? So in this step you got the remainder 0. So in this step the divisor would be the HCF. Therefore the HCF of 4052 and 12,576 is 124. Did you understand? Now we'll go for some applications of HCF. In this first problem is, I'll read the question. Two tankers contain 850 liters and 680 liters of petrol respectively. So I'll write the question for sake of convenience. Two tankers contain 850 liters and 680 liters of petrol respectively. Petrol respectively. So two tankers contain 850 liters and 680 liters of petrol respectively. Find the maximum capacity of a container. Find the maximum capacity of a container Find the maximum capacity of a container which can measure the petrol of either tanker in exact number of times. So two tankers, so this is the problem. So this is nothing but, if you seriously go through this problem, it is nothing but the maximum capacity of the container is the HCF of 850 and 680. So just find HCF of 850 and 680, that is the answer. So now solution, find HCF of 850 and 680 to get the maximum capacity of the tanker. So now as it is 850 is equal to 680 into 1 plus, so from 850 to subtract 680, 0, 15 minus 8, it is 7, right? Now 7 minus 6, it is 1, 170. So it is 170. Now 680 is equal 170 into, let us see, 4, 400, 4 7s are 28. 6. So you are getting 680 exactly. So 170 into 4 plus 0. So here in this step only got 0. So in this step the divisor is HCF. Therefore HCF is 170. Therefore the maximum capacity of the tanker is 170 liters. This is all finished.